Bien, voy a dar una breve semblanza del ingeniero Nordenson. Él es ingeniero en estructuras, profesor de arquitectura y de ingeniería estructural en la Universidad de Princeton. Estudió en el Tecnológico de Massachusetts y en la Universidad de Berkeley, California, su maestría. Y empezó su carrera como dibujante, es decir, en un estudio con Buckminster Fuller y con Isamu Noguchi en Long Island en 1974. Ha practicado la ingeniería estructural en San Francisco, Nueva York, y últimamente se ha establecido en Nueva York en su propia oficina, es decir, ya una vez que trabajó por 10 años en la empresa de Bob Arrow y asociados, y él también ha estado muy ligado con los grandes arquitectos del mundo. Por ejemplo, el Museo de Arte Moderno de Nueva York trabajó con Taniguchi, ha estado trabajando en proyectos con Kazuyo Sejima, que es una de las arquitectas más destacadas de Japón, ha estado trabajando también con Stephen Hall, tiene proyectos en diferentes partes del mundo, en China, en Europa, ha colaborado mucho con Enrique Norten, es el ingeniero que le ayuda a concebir estructuralmente sus edificios, es decir, el último proyecto del concurso que ganó Enrique del Guggenheim Museum en Guadalajara. Entonces consideramos que es un ingeniero que es muy sensible a la arquitectura, probablemente nos vaya a sorprender, porque ya, así como Barragán fue ingeniero y que iba a ser un gran arquitecto, yo creo que de alguna manera Nordenson sigue por esa línea. De manera que me gustaría que aquí empezara su plática. Antes le voy a pedir a Víctor si quiere ampliar algo de la semblanza que yo he dado, o él coordinará el debate al final.
Al final haremos una sesión de preguntas y respuestas, más o menos breve. Nada más 3 minutos, lo importante es oír a Nordenson, pero hay que ponerlo en un contexto a Nordenson, si no, no se entiende por qué Nordenson está en la Escuela de Arquitectura. Nordenson está considerado, él no lo va a decir por supuesto, pero está considerado como uno de los jóvenes ingenieros estructurales más importantes del mundo hoy en día. Y para muchos, para algunas de las élites norteamericanas, está considerado como tal vez el más prominente. Es un tipo muy joven para tener ese nivel. Ha sido galardonado con un premio nuevo a nivel semejante, es una categoría verdaderamente gigantesca, máximas contribuciones por un ingeniero a la arquitectura contemporánea. Entonces, lo interesante contextualmente de entender por qué está aquí Guy es porque desde el diplomado nos hemos cuestionado en los últimos tiempos acerca de si la arquitectura o la ingeniería no se están convirtiendo en la misma cosa. Es muy difícil poder separar hoy en día si Calatrava es ingeniero o es arquitecto. Es muy difícil saber si Foster es un ingeniero o un arquitecto, o Grimshaw o los demás. Creo que va a invertir Nordenson la concepción tradicional de cómo se hace la arquitectura y la ingeniería, visto la arquitectura como el diseño y después la ingeniería como la parte de cálculo, matemáticas y física con la que se construyen los edificios. En algunos casos él va a invertir los factores y les va a enseñar cómo la ingeniería ahora se convierte tal vez, a veces, en la génesis del diseño de los edificios.
Muy bien, muchas gracias, Víctor. La conferencia será en inglés. Aquellos que no entiendan inglés, hay traducción simultánea, pueden ir por sus audífonos, de manera que recibamos un aplauso a la administración.
Gracias. I'm sorry that I don't speak Spanish. I'll try to speak slowly so that the translation can happen quickly. I have quite a lot to show you today, and I wanted to start by dedicating this lecture to an engineer here in Mexico City that I respect very much, Oscar de Buen. I don't know how many of you know Oscar de Buen, but he is very important both in earthquake engineering, but also in the design of many important structures in Mexico City and around the country. A man of great culture as well as great engineering. I I titled this Drawing with Steel, and this will be, I think, a little clearer to you shortly. I took the title from a drawing that some students of mine did a couple of years ago of the World Trade Center, the old World Trade Center towers in New York. And it led me to think about, and I will talk a little bit about today, the work of another great engineer in the United States, Leslie Robertson, who was the original engineer for the World Trade Center towers. And the thing that interested me a great deal about his work, and in particular his work on the World Trade Center, is a degree of abstraction that exists in this work. And I think one of the ways to understand the creativity, the potential for creativity in engineering, is to understand that some of that has to do with the potential for creativity in mathematics, and mathematics is abstract. The beauty that is possible in engineering and the contribution that it can make to architecture, in the conversation with architecture, is, I think, partly in this realm of abstraction. The talk is going to be in 4 parts, not of equal length. And the first 2 will be somewhat historical. I start with this drawing by Paxton, the architect of the Crystal Palace in London. And this was a drawing that Paxton did on a napkin representing his idea of the Crystal Palace. The palace, as you all know, was a very significant work because it showed the possibility of immense space enclosure with industrialized means and massive repetition of elements. This was an inspiration for Buckminster Fuller and for many of the thinkers of architecture and engineering in the middle of the last century, who saw the possibility of making big things out of small things repeated. And this is quite apparent in this picture, this beautiful picture that shows how the glazing system and how the entire structure of this is an accumulation of small parts that are repeated. I think if you consider much of the artistic practice, particularly in the 60s in the United States, the minimalists, Solid Witt and many others, there's a lot of that sensibility present as well in this early work, and the sense of that almost intoxicating effect, both in terms of space, but also in terms of the effect on the eye of repetition. The structure was made of cast iron, prefabricated trusses, and glass that was assembled using industrial methods in the field, and it was large enough to contain trees. There was a sense that this was at the scale of nature, and in fact, nature destroyed it in the end. It burned in a fire that destroyed all the steel. This is the architect engineer himself, Paxton, surveying the death of his construction, and this was a photograph that somebody took of that during the fire, which I think is eerily like the original drawing. And so there is very strong poetic potential on many dimensions, I think, in a work like this and many other works, where the conception, the fragility of the conception, the power of repetition and the power of the means of technology and construction and industrialized methods, and then the confrontation with nature, and the coming back to the beginning, where the final form of the destroyed structure takes you back in some ways to the beginning of that work. And this, I don't think we talk about engineering in this way that often, but I think that it would be helpful to think of it that way, because there is inherent in many possible works this aspect of poetry. Another way of looking at this is if you go back pretty much in the same period of time, a little bit later than Paxton, the paintings of the Impressionists, and the way in which, in particular, Monet would show the sort of ephemeral quality of these structures. You can see on the left of this painting a structure that looks almost as if it had been designed by Peter Rice. It's this Victorian shed with cables and posts, beautiful, light, very elegant structure, and then how it's diffused and lost in the smoke. The smoke, which was also the reason why these sheds were built this way. With the advent of electric locomotives, these sheds were no longer necessary, but they were essential at a time when the smoke could suffocate you if it didn't have the space to rise up in. But what's wonderful, I think, about this painting is Monet's sensitivity to the way in which the light comes through the glass, but also through the structure, and how that light is diffused by the structure, and how the structure is almost like a fog. And this is something that Peter Rice actually understood and developed a long time later in some of his work, but I think it's already represented in Monet's painting. The sense that light and structure are intimately related. If you think about the work of Richard Feynman, the great American physicist and Nobel Prize winner, his work was entirely to do with the joining of the theory of matter and light. Quantum electrodynamics has everything to do with how electrons interact with particles of matter. And at the most essential, I think, physical nature, it has that intimate connection between light and matter. And steel has a way, I think, of manifesting that in many different ways, through its conception, through its fabrication, through the fire that makes it possible, and the fire that can destroy it in the end. The World Trade Center Tower is here in a photograph that was taken by Les Robertson not long after the construction, which you can see how transparent they were, how light these things are. They weighed 11 pounds per cubic foot. I don't know what that is in kilograms, but it's barely nothing. And they were extremely transparent in that sense. This picture obviously has a lot of resonance now. In the early work of the late 19th century by people like Larousse and others, this sense of lightness, this intermingling of light and structure was something that everyone was very sensitive to. I think that we're all aware of the work that was happening around them with the Impressionists, and they all saw the potential for how steel and light could begin to give the visual effects that they were also seeing in the paintings by their friends around the Eiffel with his works, the Gabi Bridge, which is made to be completely transparent to the light, where there is a sense of almost a fog of steel that is making up the structure, the way that the Eiffel Tower is as well translucent and transparent, and how the light comes through that. And as also in this wonderful picture, how it's in the reflection in the water, diffused as well with light. Here, a close-up photograph of the Gabi Bridge, where you can see this amazing effect where the structure is really dematerializing. It's almost like something that would now consider to be a kind of digital effect, where there is that loss of the difference between matter and light. This photograph that I took a long time ago of the Eiffel Tower, where you get again that same feeling that the structure isn't quite there. I think that is an important tradition in the making of steel structures, and one that is significant and continues to be significant and needs to be remembered in the work that we do. There are many other examples. The late Pennsylvania station in New York that was destroyed in the 1970s, a disaster for New York, that destruction of this extraordinary building that had been built in a way almost as a kind of paradox. This was a building that was modeled after the vast Caracalla, these vast masonry structures built by the Romans, and then just poof, turned into light by the miracle of glass and steel. Another tradition has to do with the sense that steel can work in tension, and therefore there is potential for this ambiguity of very skinny elements, like in the Larousse library, very skinny elements that you're not quite sure whether they're tension members or compression members. There's a wonderful essay by the late American critic Robin Evans, who writes about the Barcelona pavilion of Mies van der Rohe and says that you can't tell whether these columns are holding the roof up or holding the roof down. There's a feeling that these columns, that somehow Mies's roof could fly away if it weren't for these columns keeping it on earth. And that, I think, is, again, this potential that is available to us with steel and with the way that steel can intermingle with light. There are a couple of artists, more contemporary artists, or 20th century artists at least, that have been in the last couple of years in the back of my mind as I've been thinking about these questions. One of them is Giacometti. For a number of reasons I'll come to a little bit later, Giacometti was important for me after September 11th in thinking about the events in New York and what could be done after that. Giacometti, I think, is also important to keep in the back of one's mind when we think about steel, both in the way in which he was able to play with the relationship of volume, of masses, and of the frame around a field. Many of his paintings, many of his drawings, many of his sculptures have this frame that creates a boundary, that creates a space, something that steel structures do as well. And within that frame, then, a volume that floats. This is a great work he did early on called La Cage. This is a little bit later work of his, which reminds me a great deal of that great project that Rem Koolhaas did for the library in Paris, which was this great cube with these masses floating inside the cube. And that sense that you have this framed space created by, in our world, a steel structure, and then within that, the volumes that can interrelate, and spaces between the volumes that can interrelate. Same thing happens in his drawings, where this, a drawing of, I think, his brother Diego, there is that frame, again, that's inside the actual frame of the picture. Think about that when you think about the way in which steel structures create space. Think about, I think, Giacometti in that respect, but also look at the drawing and look at the lines and look at the way the light comes through the lines, and remember the Eiffel Tower and remember the Gabadi Bridge of Eiffel in that context as well. I want to show you, before going to Les Robertson, then a few examples in the recent past which I think illustrate some of these ideas. This is the great project of Gordon Bunshaft, the lay partner at Skidmore, Wings and Merrill, SOM, the Beinecke Library that he did at Yale University. This is a box to contain rare books, and the box floats on four corners and stands between those corners. The structure of the box is a Virendale frame made up of individually fabricated butterfly-shaped plate boxes that go from wide, where they join, to narrow, halfway between those intersections. You can begin to see the profile in that interior photograph. And then they're clad, the structure itself is clad with stone, and then between the structure are these large panels of marble that let the light through. This, again, confusion of the structure, the frame, the transparency, the effect on the light. Look at the way in which all those patterns are happening in the marble, and think back to the way that expresses something about the steel and the diffusion of the steel in the light, as well as the effect of the stone. It's a great building which I urge you to visit if you ever have a chance. It seems to float on this cushion of light at the bottom, very bright light coming in through the glass at the bottom, which has no shading or anything on it. Another project a few years later, in the early 1980s, by Renzo Piano with the engineer Peter Rice and Tom Barker, the Menil in Houston. A project which had the use of cast iron. Not cast iron in the traditional sense, but actually a kind of cast iron called ductile iron, which uses a slightly different chemistry, which was used to make these trusses, which were then connected to ferrous cement leads that were integrated within the structure. The entire assembly designed completely for the diffusion and distribution of the light into the gallery space. Extraordinary project, very disciplined, very clear, and a very important example, I think, of what happens when you have this blessed conjunction of a dedicated and sophisticated client, young and energetic and ambitious architect, engineer, all working together, museum director who was a visionary, all of them coming together to make a great and wonderful project, which I think is unique for all of them in their career. The last project that Peter Rice did, Peter Rice being the great Irish engineer who worked with O'Hara from the 1950s to his death in 1992 on the Sydney Opera House. He was the designer of the great glass walls at the Sydney Opera House. If you go to Sydney and visit the Opera House, pay attention to the walls and the way in which the glass comes together, mitered in the corners, the way the steel has been designed to support that glass. It's a brilliant design that isn't often observed because people are so focused on the rest of the building. So Rice had a great career working with Renzo Piano, and then working on a number of projects through the end of his career with the railroad company of the SNCF in France, including the station that he did for the Charles de Gaulle Airport, which was this really almost delirious expression of the way in which you could pull the structure away from its purpose in the roof and make the structure actually completely occupy the space and become this kind of forest where the light would come through and be affected as if it went through a cloud. Scattered is, I think, the best word to describe the sense of scattering, which I feel is a very precise sense in physics of what happens to light when it goes through a cloud. But scattering also in the sense that you lose any sense of order in the way in which the light and the steel are mixed together. I don't have a slide of it, but there's also a beautiful project that Rice did with IMP at the end of his career, which was the roofs over the Louvre courtyards on the North Wing in Paris, which again have this ability to take the light and dissipate the light without casting any distinct shadows on the sculptures below. The next part I want to talk about is Leslie Robertson. Robertson's an engineer who worked in California and Seattle, Washington, and then he moved to New York to design, to be the chief engineer of the World Trade Center towers in New York in the 1960s. And Robertson is a very interesting figure, I think, because unlike Peter Rice, who was very interested and concerned with objects, like Renzo Piano, Peter had this sense that it was possible to make this kind of Victorian craft expression. Rice often talked about the trace of the hand, of how in the Pompidou Center or in the Menil, you could see how a craftsman had made the thing, and you could tell the differences that existed because of the different craftsmen that had made the different parts of the project. And that was a very important humanist dimension for him as someone, I think, who was very influenced by the Victorian ethics of William Morris and others who said that the worker was a significant member of the design process and that the hand of the worker should be made visible in the work itself, that you should be able to tell that another human being had made this thing that you were occupying. Robertson is not like that. Robertson is much more cerebral. It's not about the eye. Sometimes I think it's a difference that some people can understand better if you make the comparison between Picasso and Marcel Duchamp. Duchamp, who was an intellectual artist who thought about what he made and made things that were meant to be thought about, not things that were necessarily meant to be looked at and enjoyed just through the eye, but also enjoyed through the mind. We did this drawing a couple of years ago, actually a year and a half ago, for an exhibition on tall buildings that I worked on at the Museum of Modern Art, and exhibited this drawing after time. It's done by a group of students that took the original drawings of the towers and colored the steel according to the type of steel that had been used. One of the things that Robertson did was to use 14, not 10, but 14 different types of steel on this structure. This is completely unheard of. Typically you use one type, maybe two, but less use 14 types of steel, and you can see, I'll show you a close-up, in the middle of that column is a color coding of the different types from normal steel, the kind we use every day, to very high-strength steel, which in this case was about 3 times as strong as this normal steel, with lots of grades in between. So what we did was we went through the elevation of the 2 towers, and we colored in each case, the steel that had been used there. And you have this pattern, which I think is one of the most beautiful things I've ever seen, which is a manifestation of an idea that until we did this drawing had never been visible before. Was obviously hidden, as structure usually is, behind the architecture, but it was also hidden behind the structure. You couldn't tell that this difference existed in this object unless you actually took the drawings and did this mapping exercise in order to understand that. And I think that is a kind of intellectual achievement and a kind of sophistication that is really worth paying attention to and thinking about. And not everything we do is about the eye, but some things are also about the mind. So in the middle there is this scale of the different types of steel. On the top, it's hard for you to see, I know, is the different parts that were made up, that this thing was made of, and I'll show you some close-ups of that in a minute. Again, this is the picture as a whole. This is the close-up. Actually, those of you maybe a little bit older who remember Bucky Fuller and remember perhaps this drawing that he did, the Dymaxion map of the world. I intentionally laid this thing out so that it had the echo of that Dymaxion map, very symmetrical. And, so there you see on the bottom the lower part of the structure and the different types of steel. The stronger steel is concentrated toward the edges, and the less strong steel is concentrated toward the middle, but not in a symmetrical way. And that's because there were 2 towers, and because the wind is different in New York. There's more wind from one direction than from another. And so when you add the different directions of wind and the position of 2 towers next to each other, where one is slightly to the northwest of the other, where you understand that the wind often in the winter tends to come from the northwest, so one tower is shielding the other tower. You begin to realize this complexity that there is in this environment, which is a complexity that in this case is mapped onto this structure. Toward the top, you have more intense variations as you go around. Again, these at the bottom show you which tower, in this case, which side of which tower is being mapped. But I think it was quite moving to see this and to understand how much care had gone into, how much intelligence, how much intense creativity had gone into the making of these things that had been destroyed. So as I said, to my mind, one way to understand this is to think about it and really to lean on the critical literature that is available on someone like Duchamp, because there's not very much people writing about structures this way, but there are some analogies, and I think it's helpful to keep those in mind. Let me go through just a few examples of Robertson's other work that led up to the towers. This is a project he did in Pittsburgh with Harrison, Wallace Harrison, for U.S. Steel. It was designed in this shape with these notches in the corner, in part as a way to respond to the wind forces. It had very large columns on the outside that were actually connected to the building every 3rd floor. And so they were kind of a mega structure supporting this. And they were large, and they were made up of plate, custom made of plate. The interesting thing is that Robertson even here chose to make the outside plate a stronger steel, 50,000 pounds per square inch strength, and the inner plate a weaker strength, 42 pounds per square inch, and that in order to get a certain balance in the way that that was functioning. He also here, for the first time, started to do this, what I call painting with steel, where he was using different types of steel in order to direct forces into a truss where he wanted them to go. Now, here is where there is a paradox. If you wanted to take a force from one place and move it to another place, the best way to do that was to make the path where he didn't want the force to go strong, and the path where he wanted the force to go weak. Think about that, that's completely counterintuitive. And the reason is that if you use a very strong steel, you need a smaller member. And if you have a smaller member, it's less stiff. And if it's less stiff, it will take less force. If it has a choice to go somewhere else that's stiffer. And so weaker steel has to be bigger steel, and the bigger steel then takes the larger force. And so the painting here is a way of using strong steel to avoid force. I don't think that's a very intuitive way of going about things, and I think that is evidence of the sophistication of this kind of thinking. The IBM building that he did in Pittsburgh used to some degree a certain variation in the steels, and actually I think the painting here to some extent, the painting of the steel actually exhibited that to a degree. I think they used different color primer to make sure that the workers didn't confuse the pieces. It was assembled in a way that you'll see again with the World Trade Center in this kind of prefabricated, completely customized way where each element was made specifically for its place. Very much like, I mean, look back on this, very much like things that you see now. You know, the work of Herzog nowadays has a lot of similarities to this kind of work, but the engineering of that work, for the most part, I don't think is as sophisticated as what Robertson was doing at that time. So then the towers for the World Trade Center themselves. This is the wind tunnel model that Robertson had. This is the towers under construction. Notice here on the corners how not every level has a column, and the reason was that they left those open to allow access for materials to come in. These frames were pre-assembled. The plate was, a simple plate was used as a beam on the backside, and then the columns were boxes. The columns were 40 inches apart, 3 foot 4 inches apart. So each one of these units was a 10-foot wide unit. The steel that was used, which you saw earlier, included 14 different varieties of steel, was consistently used, well, the same size at any level. So what was happening was that the plate that was the beam along the edge, that plate, had the same thickness as you went all the way around the building. So it was the same thickness plate, and the columns were the same thickness column. But if there was a demand for one to be stronger than the other, or there was a desire to make one less stiff than the other, that's where then Robertson would paint it with the steel. And so he kept the dimension the same, but the material different. And that's where this painting of different types of steel came into play. At the lower levels, there were these columns that were quite heavy, that had this kind of Gothic quality that Yamasaki was interested in. You see them there. We didn't map those, actually. Our map information we had was above that line. This is them in fabrication. This is them in transport, this wonderful train of columns going to the site. This is Philippe Petit drawing a line between the towers and walking across. A few other projects of Robertson's a little bit later. This is you know this Philip Johnson project, which he was an engineer for. Johnson, who really had no interest at all in engineering, did get Robertson involved in this somewhat complicated project, and these aren't the best images, but there is inside this otherwise postmodern object a very intelligent structure that's worthy of study. Another project later on with I.M. Pei, the Bank of China in 1989 in Hong Kong, which is the first sort of space frame crystal structure that they collaborated on. I am having this idea of this crystal sitting on a base very much like the objects that Chinese mandarins would collect, and less than he working on the development of that crystal into this modulated structure that folded back into itself as it went up. The central column at the upper level is disappearing when you get down to the bottom because it's held up by those diagonals that come into it. Interesting predicament was for Pei, it was very important that the geometry resolve itself in the surface of the building. And so where diagonals met verticals and met each other, those lines should come together at a point on the surface. Well, the structure is not on the surface. The structure is back from the surface. And so what Robertson then invented was this idea of gluing the corners together with concrete. And so because the geometry was what it was on the surface, it was then something completely new on the inside where the elements didn't actually meet each other, but just reached a point where they could get and then were enveloped in concrete and glued together. I want to now, I think, talk first a little bit about some projects of mine. Am I going slow enough? Yes. Okay. Looks like I'm going too fast. The projects I want to show you include projects that I worked on when I was at Arab in New York, and then some projects that have happened since I left Arab about 8 years ago and started an office in New York. And they're all steel projects. I've not included any projects in concrete, and I've excluded a lot of projects that didn't quite relate to this idea that I'm trying to discuss about drawing with steel. This is just one image of a chapel that is next to the Menil Museum in Houston. The architect, François de Menil, is of the family that also commissioned the piano project. And this was a chapel inside a building where the chapel is a glass recreation of a chapel in Cyprus where there were these two frescoes that are now located here. The thing that was, from a steel point of view, interesting about this project was that we created a kind of spider's web of steel bars that are about 2.5 centimeters in diameter, which you can see some of the black lines. And this web was stretched between the roof and the floor, and so it was like this tight spider's web, which we then inserted the glass panels into. And that is, when you go there, if you go to visit it someday, and you grab a piece of steel and shake it, you'll see how remarkably stiff it is because of the tension that we put into it. Around the same time, we did I did a project also at Arab with the architects Smith, Miller, and Hawkinson, which was a little canopy at an airport in New York, which was a kind of homage to the Menil, where we mixed the idea of taking a leaf with a steel structure, where the leaf in this case is actually made of panels that are plastic, they're epoxy, with carbon fiber and glass fiber in the plastic. It's actually a layer of about 2 centimeters or so of honeycomb, very light material, on the outside of which is only about 1 millimeter of epoxy, inside of which is a system of fibers that go in all different directions and that reinforce the structure like a reinforced concrete structure. And these are placed then on a steel structure of cables and struts, which also includes glass. So it's a bit of a mixture of different things brought together to make this light canopy over these ticket counters. The beauty of this is that it looks very fragile, and no one dares to touch it. And if it weren't the case, as you know, at many airports things change a lot and they tear things down and they build new things, and the new airline decides on a different marketing image, and so they want to change everything. The beauty of this thing is that it was built for one airline and then taken over by another airline, and they were afraid to touch it, and so it's still there after many years. This was in Santa Fe. I had to show this here, right? This was in Santa Fe, New Mexico, the Santa Fe Opera House, which has a steel structure of rods and masts that has a kind of interesting geometry. It basically looks like you take 2 fingers like this and bring them like that. You have these masts that reach out from existing columns, and then from which there is a heart of cables that supports the roof. The roof is actually made of wood, which has nice acoustic properties, and it's open on all the sides, so when you're sitting there, you can see the valley around you. The challenge was to build a structure that was light enough, but larger than what had been there before, that could sit on existing columns and foundations. This is a part of a series of projects which are, again, having to do with this sort of idea-driven work, that there is an idea that is of interest and appealing, and that we look for an opportunity then to transform that idea into another material, into another occasion. In this case, an idea that Palladio used and others at the same time in the Renaissance to build stairs that have you can see this is on the right is actually a stair in Greece that's similar on the left as the Palladio stair at the Accademia in Venice. But then the principle is that you have a series of blocks that are resting one on the other. And what that does is allow each one to support the one above it. And because it has weight from the top on one corner and support from below on the opposite corner, there is a twist, and that twist has to be resisted by the support in the wall. But because of the mutual support, the stone doesn't actually have to act as a cantilever. You know that stone is not very good in tension. So if you just stuck a piece of stone from a wall, it would probably break. But if you lean each stone together, then that sharing of the load as it goes down takes most of the load down, and the small amount of stress that comes from the torsion can be resisted by the stone back into the wall. And that's what Palladio used. That's what even before that the builders of the Santa Theater in Greece used. And it's been applied in various cases ever since. And I think it's a beautiful principle because it is, again, one of these situations where it's not quite obvious what's going on, and it's something that you have to stop and think about to understand. And so this was a stair that we did using that same idea in steel and glass with the architects Adam Urinsky and Steve Cassell, ARO, Architecture Research Office, they're called, in New York. And there we took this notion and we said, well, we'll take the torsion out in a thin wall of glass, and we'll connect the part of the stair which we make into a steel tube through the glass, and then connect each of those with a plate of aluminum that would establish the continuity from one step to the next, that would allow it to work. I call it a cascade, you know, like a water cascade, that would allow the load to cascade down from step to step. We couldn't have solid blocks because then we wouldn't have any glass left. So we had to separate the tube vertical element from the horizontal element so that the tube could go through the glass and there would still be some glass left around it. This is when it was installed, very heavy pieces of glass. You can see the holes there in the glass. The glass was actually laminated 3 layers of glass, all of them tempered, where the inner layer was the one that was doing the work and the outer layers were really there for helping against buckling. So there you see some of the computer testing and how the holes were done. We also did some full-scale tests in the laboratory, and that's the way the connection was made. In the hole, there's actually a little U-shaped shoe that goes on either side of the glass, and then the black there is a piece of plastic that gets, there's a sort of 2 sheets like this, and when you push them together, they expand, and that jams the thing into the hole. We left a gap above the tube, you can see the space there, so that at least an engineer that was coming over for cocktails who looked at that would then say, it's not cantilever. Another detail that you can sort of see in the back there's a little stud with a slot, and that is because if you made a connection at the top of the stair that was rigid, then the stair would actually just want to lean against that and not behave the way you want. But we wanted, in case somebody destroyed the glass, for there to be that possibility so that there would be some additional safety. And so we made that connection, but we left the slot and made it very visible. So again, the engineer with the cocktail in his hand would be able to recognize that idea as well. This is a bit more mischievous. What's the word in Mexican for mischievous? I remember that. This is a competition for a bridge that we did a couple years ago for a bridge in Hong Kong. And we actually made it to the finals, but we didn't win. The principle here was of a tower that was made in cross. And if you know that there is this great thing in China called Feng Shui, which says that crosses are really bad. This was obviously not going to win, but our collaborators in China were saying, bad Feng Shui. So our engineers were rational. We don't engineer Feng Shui. So the plan shows you very clearly what's happening with the cable structure. In elevation, it really looks like any other bridge. It's long, it's 1,000 meters long. And we created this crossing over of the cables, which helped to stabilize the deck by having that angle to it, and also helped the cables because where they crossed, they could be connected, and so that reduced some of the vibration problems that you get with long cables fatiguing as well. So there was the bridge that could never win. This was at SciArc. We did an exhibition about a year and a half ago called Camber. Again, an idea project. Here, what we were trying to do was to build a beam out of steel that would be very, 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 very thin. The span that we had were between 2 cables from the ceiling that were about, I'd say about 30 feet apart, with cantilevers beyond that of about 10 feet on either side. And the entire beam was going to be about 4 centimeters deep. So impossibly skinny element. And what we wanted to do was figure out a way to make it out of very small strips of steel, bolted together, made in a shape. You see on the left, we built this wooden form, and so made in a shape that was exactly the opposite of how it would want to deflect, so that when you hung it up, then it would come out dead flat. And the test was, to the eye, well, this seems strange, that this thing so thin is completely flat. Now, we had failures. This is a case where there was a shear failure in the first one, and it just didn't work at all. We didn't have enough rivets connecting it together. So that one in the back there, you can see we repaired the failure with these clamps, but on the other side, on the right, is where it just fell down. So we left that the way it was. The second one, we had some testing and we found that we needed to do more clamping, so we put it up with the clamps in place. Sorry. So you see that one behind, and then finally the third one, see the second one there on the right, didn't quite work, and then finally we got it right with the third one. And this was a project that involved a lot of students from SciArc. Took place for a period of about 3 weeks, building something strange and illustrating something interesting and driving everybody nuts. But it was really, I think, worth it. I don't think anybody quite understood the project. The SciArc crowd that came to the opening was looking at this thing and didn't really quite see the point of the project, which I also enjoyed that element of puzzling. Of a more, if you will, noble, but similar actually in some respects, is the project that Jorge mentioned earlier. It's a museum of modern art that we worked on with Taniguchi. We were just the design engineers working with Taniguchi, and then there was a team of architects and engineers in New York that collaborated as well on the execution of the project. And it was really a remarkable achievement, because building something wonderful and highly crafted in New York is almost blasphemous. There is a religion in New York that says that it is impossible to build anything good, that it's necessary that all things in New York should be badly built, should be ugly, and should be commercial. And this is a religion that is believed in by many of the powerful figures in the city, many of whom are developers, who believe that all that can be built is mediocre. And so we had a big challenge as a group, not just Taniguchi and the design team, but also the associate architects that included people who had worked in the past on projects like the Louvre, etc., and the contractors, to prove that it might be possible in New York to do something that was much more refined. I don't think that it was successful 100%, but I think that to some extent it worked. And the reason it wasn't successful 100% was not because it was impossible, but simply because those people who have that religion made it impossible to prove their point. The projects which we were involved in the sort of early stages, and really the basic thing that we did was organize the structure according to a simple grid that was actually had a nice proportional relationship based on sort of rectangular tatami proportions. So there was a simple sort of order to the structure, even though most of it was hidden behind the walls. There is an interesting moment in the contemporary gallery that is behind there, where you see the Monet water lilies. On the other side of that wall, there's a very large contemporary art gallery. And one of the things that happened during the design period was that we were talking about that gallery, and one of the, I think the director at one point said that he wished that somehow this gallery were completely open, that there weren't any columns in that gallery, and there really was only one column that came down within the space. The space goes from 53rd Street to 54th Street, so one entire New York block. and it's about 20 meters wide. And so in the middle of that 20-meter zone, there was this one column that came down from the tower that you see behind there, helping to support that tower. Well, as it turned out, it was at a level just above the top there, where the tower begins. The service level, where we had a truss that was built to help to stiffen the vertical bracing that was around the elevators and the stairs on the backside of the building down below to support the contemporary art gallery. And so in the gallery itself, in the contemporary art gallery itself, there would be no columns, and there would be this vast space, even though there was this very large building above. So we did that, and interestingly, because the structure was already there, all the costs associated with the fabrication of that structure was already in the budget. So all we were doing was just making a little bit thicker everywhere. And the cost of that material is just a small part, maybe a quarter or a third of the cost of the steel in place. Because, you know, you buy the steel, you fabricate the steel, you transport the steel, you erect the steel, you make the connections, and all those things cost. Well, if all you're doing is just making things a little thicker, you're only affecting one part of that cost. And so I was able to say that the additional cost of getting rid of those columns was $10,000. Everybody thought I had performed a miracle. And ever since, there were tours organized during the construction where people who had no idea about architecture or engineering were brought to this place as if a miracle had occurred there, and we're told, now this is where the column was removed, and these poor people were there sort of staring at space, wondering what they were supposed to look at in the absence of this column that this miracle had caused to disappear. So we had this little shrine there for the miracle of the missing column. So that was one thing that we did, which was mercifully invisible. The other thing that we worked on was that stair, which is visible. And then the last thing which I want to show you, which I'm proudest of, is the wall that you can see there through. Now this is, you can use the Barnett Newman as your point of focus. This is now looking the other way, past the bridges that go across, which were impossibly thin, and then over to this glass wall, where you see here from the outside, which was also impossibly thin. And this was a lot of fun because the wall was very much Taniguchi's idea and based on a very beautiful wall that Taniguchi had done at Ueno Park in Tokyo, where he has solid steel vertical mullions, that are welded to horizontals in a grid that is absolutely beautiful and crafted like nothing you've ever seen. Just everything is precise, and all the welds are invisible, and everything is straight. And Taniguchi, having heard all the religion about how impossible it was to build good things in New York, was adamant that it would be impossible to do anything like that in New York. And so the discussion back and forth over a long period of time was whether it was going to be possible to make these also out of solid steel mullions, or whether they would have to be covered with aluminum and made more precise because of the quality that could be achieved with the aluminum. Of course, I was arguing for the solid steel and doing everything I could to make it possible, finding the fabricators, finding the people that would put it out, organizing the process, and being as convincing as I could about the idea. In the end, and really what I was anticipating, and I think it was, and what was achieved, and what I think Taniguchi understood very well, was that if you could make this impossibly thin, and these are 5 centimeters wide, and if you look at the left-hand most vertical, that's going up 20 meters. So this is 5 centimeters, 20 meters tall, and to the eye, I think, when you look at this wall, it looks wrong. It looks too thin. And it does something unusual to your eye, I think, in being a surprise in that sense. So that's there, you can see the steer on the right, and that's that mullion that goes all the way up to the top. The other ones are supported by little props. They're continuous all the way to the top, but they are supported at that floor above. And they're 2 inches wide, 7 inches deep. They're solid steel. And the connections between the horizontals and the verticals are made like carpentry. They're not welded together, because the problem would be if you welded it, that it would distort. And this was the worry that Taniguchi had. And so instead, we came up with a connection where things were cut out so that they would fit into each other, sort of like traditional Japanese carpentry, and then get bolted together, all of it happening from the front, so that when the glass was then attached to the front, you wouldn't see that joint, so that it does look like it's monolithic. Now, from an engineering point of view, the problem with this, and there you see the one that goes clear up to the top, and then the other one's there to the right. The problem with this thing is that it wants to buckle as an entire frame to the side. And the reason it wants to buckle is that it's actually not connected to the tower on the left, because we needed to isolate, we have earthquakes in New York, believe it or not. We needed to isolate the new building from the old tower. And so the connection at that is a very soft spring that holds things more or less in place in the wind, but it's quite soft in an earthquake, which means that there's no resistance on that side to buckling. So then the entire assembly of this wall had to work as a frame connected together with moment connections done with these Japanese-style dovetailed joints, so that it wouldn't buckle in that plane. And that was the challenge from an engineering calculation point of view. And I was very happy that in the end that's what was built. There was a scary moment when at some point somebody produced a sample of a bar of steel, and it looked awful. And so the architect said, you know, see, I was right, we can't do good quality work. We have to wrap this in aluminum. And so then the design went for a while in the direction of being wrapped with aluminum, which would have made it much thicker. Not much, but at least 1 centimeter all around. Then somebody realized that if it was wrapped in aluminum, the moisture that would get trapped inside, because it's a museum environment, would get cold because of the contact with the glass, and that cold would then cause the moisture to condensate, and you would have you'd have water accumulating on the inside between the aluminum and the steel. And to prevent that, there had to be a way to generate some heat. Well, the space was too small to generate heat, and so the only way to generate heat was actually, and somebody proposed this, not me, pump hot water through the solid steel. Well, then the contractor said, no, wait a minute, you can't do that, because if you take this wall of solid steel and you drill holes through it and you start pumping water through it, it's not a structure anymore, it's a radiator. And if it's a radiator, the plumbers are going to want to build it. And that killed that idea. This project was a competition, and it's part of a series of projects that we've done where we've been in collaboration with architects in if you will, symmetrical role to the normal condition. Most of the time we collaborate with architects, but the architect is the leader and is the person that decides what idea is going to be implemented in the project. Maybe some of the ideas come from us, maybe some of the ideas come from other people, but the captain of the ship is the architect, and the architect makes the decision about the direction that the ship is going to take. In these cases, we've been invited to participate in the competition ourselves, but we've decided not to do it alone and have invited our friend architects to collaborate with us. And so the difference really is only that in these instances we're the captain of the ship and we collaborate with our friends. This is a project which was a competition for a roof to cover a building in Washington called the Patent Office Building. And there you can see the courtyard. I'm sorry, to cover the courtyard. And so to make a little bit like the British Museum did in London, to make this covered courtyard that could be used as a public space by the museum. The museum used to be called the Patent Office Building. It's now the Museum of American Art and also the Portrait Gallery of the United States. So the portraits of the presidents and so on are in this gallery. This is the way it looked in the past with 2 trees in it. This had, by the time we did the competition, this had been destroyed because they built an underground space, and so they removed the trees and removed the landscape. So we were dealing with a hard open space in our project. We worked with Harry Cobb, who is a partner of IMPay, and together we proposed this scheme, which was based on having columns that were positioned in the space at diagonal points, not where the trees used to be, but similar relationship to the trees. We actually switched the diagonal points from where the trees were. And we felt this was important because the quality of the space, in our view, had been very much improved by the presence of these trees. It's not a very beautiful space. The shapes in the space are kind of unplanned. And so the trees had a way of reconciling those parts and making it much more attractive. And so we wanted to continue that effect with our columns. We also then had the benefit of being able to support the structure independent of the old buildings, which were not really designed to carry this load. From a sort of structural concept point of view, we said we would take these points that were coming up to support from the ground as the 8 support points. We would put a grid on top of those, and we would then calculate for weight of the structure, the glass and the steel, what the distribution in that grid was of moments. So, using that distribution of moments, we then were to generate a geometry of open pipes, of pipes that would rise and fall according to the dimension of those moments in both directions. So you have this geometry that reflected directly the way in which gravity was affecting this grid. You then had the grid itself, which contained glass, and then below that supports between the grid and then the columns below, and finally the project. So this, you had the grid, you had these 3 columns coming out supporting it, and then this bubbling cauldron of structure that was coming up and down above and below this grid. This is a good representation of it, where you see this amazing thing that as you look around it from all different directions looks chaotic, but in fact is a direct reflection of the order of gravity on the system. In my mind, this was a continuation of this idea that I talked about earlier of a way of diffusing light with structure, of making the structure into a kind of cloud. And in fact, some of my colleagues who were also in the competition had a similar idea, and a number of the projects were actually organized around a way of marrying the shading and the structure in different ways. One that won by Norman Foster is a very beautiful kind of wave structure where the dimension of the ribs varies as a function of the light. And this is what you would have seen from the street as you went by. It's kind of, I think, somewhat humorous also structure as well. The final part of this is related to the World Trade Center, and I just wanted to talk to you a little bit about different projects that have involved us since 2001 in different ways around that location. Somebody yesterday, we had a discussion yesterday afternoon with some of you, and somebody asked me about where I thought things were and where I thought things were going at the World Trade Center site. And I think that it's clear to everyone that the process has been hopelessly disorganized, and that in particular the government is guilty of being very disorganized in the way that they have tried to respond to the reconstruction of the site. But I think in the long historical sense, that's probably a good thing, that that paralysis has allowed things to slow down, has prevented bad mistakes from being made. I think the master plan that was originally proposed was the right, not a very good master plan. And I think that time has allowed people to criticize that plan and to modify it and eventually probably to improve it. I think the ideological debates that are going on are very good for New York and for the country. I think it's very interesting, for example, that there has been this ideological debate about the so-called Freedom Museum, where both the right and the left are attacking it. And I think whenever you have something that can create that kind of hostility from all sides of the political spectrum, then something interesting is going on. So that, to me, that delay is important, and hopefully that delay will continue. Our experience working there basically in 3 episodes, really one every year since 2001, and I'm just going to briefly talk about them with you. The first period was actually right after the attacks. There was an organization that I helped to establish in New York called the Structural Engineers Association of New York, which was modeled after a similar organization in California. And those of us who had organized this group about 4 or 5 years, actually more like 6 years before, were in touch with each other, and right after the attacks, and were trying to find ways that we could organize our colleagues to help in whatever way we could on the site. We eventually did get organized within a couple of days, and starting about 2 or 3 days after September 11th, there were groups of engineers helping on the site with the city, with private groups that had already been put in place. I think, you know, when we look back now on the catastrophe of the Katrina hurricane, it will be an interesting time to look back and see why the response in New York was so much more organized. I think the extent of the devastation in the south of the United States was much, much larger than in New York, where it was more localized. But I also think that the preparation in New York, both among the private and public agencies, was better than in the South. And I think that reflects a lot of the attitude that people have about the role of the city and the city government in the making of stability in the city in different parts of the U.S. I think in the South, in the U.S., there's still an attitude that everybody's on their own and everybody takes care of themselves, and they all carry a rifle and they all do what needs to be done. And that's not really the way you keep a civilized society together. I think in New York, where we don't all carry rifles in the back of our pickup, there is a little bit more of a sense of community and a sense that maybe we organize through our city institutions to get things done that need to be done. So a lot of interesting discussions I think are going to happen as a result. The federal government didn't really do much in New York. Fortunately for us, Bush stayed away most of the time, and we were left to take care of ourselves on our own. One of the things that we in particular initiated, and this was something actually that came from my experience working in earthquake engineering, and actually coming here back in 85 after the earthquake, learning how one responds to a disaster in an earthquake disaster, and trying to apply those lessons to the situation in New York. And one of the things that I realized after I arrived on the site was that, of course, everyone's attention was focused on the towers themselves and the destruction there. There wasn't very much attention being paid to how you would go about determining whether the surrounding buildings were safe for people to reoccupy. And so we organized a group of engineers and architects that within a day or two assembled into groups who then went around to the different buildings around the site, and after 2 days of pretty intensive surveying, came back with forms that had been filled out, similar to forms that had been developed for earthquake response in California, and a kind of triage of the buildings. Is this building, no question, okay? Is this building maybe okay, but I'm not sure? Or is this building, for example, B's, sufficiently destroyed that we shouldn't allow anybody into the building? And that kind of separation would actually allowed us to reach the conclusion pretty quickly that 90% of the buildings were fine, and to convince the city that that was the case, and to allow people then to return home perhaps sooner than they would otherwise. These are the two buildings right next to the site that were not so okay. One of the things that we did was go in and investigate those buildings and look at what the damage was, and to see also how deep the damage was. And it turned out the damage wasn't really that extensive. It was really concentrated near the front, but it also turned out that the damage was quite different to the older buildings and the more modern buildings. And a lot of that had to do with the ability those buildings had to withstand fires. Published a book, which I will send you for your library. I don't think we have one here. But we put everything together in a book, and this is really the only record that exists of photographs and analysis of all the buildings surrounding Ground Zero. And this is actually, we published this ourselves and found a printer in China and printed it and so on. So it was, a case where there was an opportunity there for private people to actually make some contribution to the city, but also to the historical record. The second episode was initiated by the New York Times Magazine, which on the anniversary of the attacks published a series of ideas for what to do with Ground Zero. The inspiration for this was the frustration, even then, with the mediocrity of what was being proposed at the time. This was, for me, also where Giacometti came in. The sculpture that he did that's called City Square, which is part of the collection of the Museum of Modern Art, was in my mind a lot. And it represented for me, in different ways, the spirit of what I thought could be both an approach to the dialogue, but also an approach to the architecture that was possible. There's a silence, I think, that's associated with Giacometti's work. There's also an attention to the space between people, I guess, analogous to the silence, and a kind of ephemeral representation of individuals themselves. In that spirit, we contributed some ideas to the site planning ideas that were being discussed during that New York Times exercise. We worked on this, so the notion of trying to pull as much of what might get built away from the site, and then playing around a little bit with the notion of a structure that twisted, a little bit like a Noguchi lamp, and understanding how that might have an effect on the structural behavior. And for the engineers who are interested in tall buildings, one of the things that does is that, if you think about a tube like the Hancock Tower or the Sears Tower or even the World Trade Center towers, a tube works because the columns are very closely spaced around the perimeter. It's almost like a solid tube. So when the wind blows in one direction, the front is in tension and the back is in compression, and the sides take the force, the shear force. Well, if you take that tube and twist it, then what's front and back at the top becomes the side at the bottom. And so you then have this very interesting mixture of what is happening in the tube that comes, kind of mixing of those forces that comes from that twist. And that's something that did actually add a little something to the resistance of the structure. In addition to that, twisting has an effect also on the way the wind goes past the object. Something that Calatrava is actually also investigating with his tower that he's doing in Chicago. So that was a focus on towers around the site, but also we were interested in exploring ways in which you could take functions from the site. And this was really the main discovery of this New York Times project that Herbert Bouchon organized, was the idea that you pull away from the site some of the function and clear the space and let the space be more open in the short run and maybe even in the long run. And one of the functions that we then took on, and this is another project where we collaborated with Harry Cobb, was the idea of a new kind of tower that could be used for the broadcast of television, but also would have a symbolic quality to it. The notion of this tower, which was that it would be made in a way that was not hierarchical, that didn't go from a base that was large to a top that was pointed, but was the same at the top and the bottom, and they would be made up of elements that were in a kind of conversation with each other, 7 stems going up and moving past each other in a geometry that responds to the wind effects, linked by these beams that never close, that are always open, and that create, therefore, a structure that has a quality, I think, that in some ways remembers that sense of the space between things that that Giacometti has to teach. I'll come back to that in the end. The next project that we got involved in was this design for the tower that was briefly known as the Freedom Tower, which is the name I thought was ridiculous. It's an office building. It's not, no. But the Tower of Greed, maybe, or Tower of Money, but you know. But the anyway, we did have the opportunity to work on this for about 7 months, and it was a good opportunity for me because we had the occasion basically to replace what I thought was an awful design for this tower, a design that I didn't think had very much content to it, that was mainly propaganda, and that this could then show, at least at an intellectual level, an alternative to it. The notion was really related to this idea that started with Noguchi, and actually before him, I think, with Brancusi, of a twisted object. But the difference was that we could locate that object on a site here, which had a shape similar to that building there. And so instead of taking a form and twisting the form as a whole, the opportunity was to take actually just 2 sides of that form and turn it. And there was some nice echoes of what's done in construction in New York with concrete columns, where a corner, if you look at the concrete buildings in New York, the columns get larger at the bottom and smaller at the top. But instead of being centered around themselves, they're actually organized around one corner because it's easy to locate them that way. And so the corner is what goes up and down vertically in construction in New York. And so this was a nice little echo of that, and many, many other sort of little private homage embedded in the design. But it was going to be a bottom half building, and then another 40% or so in 30% or so in structure, supporting then above that an area where you could locate antennas. So the form, as you can see here, the corners where the number 4 is stay vertical, and the corners where the number 3 is move in that way. So at the beginning it's 200 feet this way, it's 260 feet that way, and then at the top it's again 200 feet that way, but narrow. So then as you look around this thing, you then have a different shape as you move around. So something that I like very much with the Sears Tower in Chicago, that it has that sculptural quality that changes as you move around the city, sometimes thin, sometimes almost like a figure, almost like those, somebody last night was mentioning the Greek statues, where, you know, the early statues, the Kuroi statues, where the boy takes a step and the body turns. So there's a bit of that from that angle, and so on. This is a model that we built, which the Museum of Modern Art bought. So now we have that in a nice home, in some closet somewhere. So, building cable structure, the purpose of which is to support a zone at the top where the antennas could go. Very tall, probably too tall. In the end, the governor of the state, New York, decided that he thought it was too tall, and so his decision was to cut the top quarter of it and then change that design from there, and that's the design that you're familiar with. Part of the homage was to the structures of New York, the construction of the Brooklyn Bridge in the cable structure, but also the construction inside the Statue of Liberty. There was a lot of talk about the Statue of Liberty as a symbol. I thought it would be interesting to talk about the structure of the Statue of Liberty as well as a symbol of a kind of dialogue that's possible between form and structure. The building sits in a difficult site because it's right above the tracks, and one of the beauties of this triangulated structure that you get is that it allows the building actually to be a bridge, and you can remove columns where they fall on top of the tracks. And there you can see in this plan the core in the middle, which is just a concrete core of the down building. So the typical floor. There you see the structure. The diagonal structure is the continuation of that angle of the slope of the side that goes up. So you're just repeating that angle, which is 1 to 10 across, and then joining into a symmetrical column in the other direction. The top structure is made of cables supported by these two concrete masts, and at the top is a carbon fiber, actually, segregated structure, which is really just symbolic, within which are the antennas. We did a lot of wind tunnel studies on this thing to see how it behaved. It's a very unusual structure, being so open in the top, and it did have some interesting properties. It was actually quite stiff torsionally, and all the results that came in were very positive. We did some studies together with the mechanical engineer and the architect on how you could put wind generating turbines in the structure and whether or not that would affect the wind response. We were able to sneak in a little peace symbol in there as well. There you can see the truss at the top. So this is the cable system that connects between the top truss down to the top of the building. So you're pulling up on the building and pulling down on this truss at the top to make the tension in the cable. You're using cables because they're small, and that way you don't have any obstruction to the wind and you don't have unnecessary forces. This shows you how, when you pull up, you're actually pulling up the socks of the building. So the outside steel is getting pulled, and that force is coming down through the concrete spire in the middle. The nice thing about this kind of a cable system, which is adopted from bridges, is that the cables can be installed through jackets that can be lifted, that are very easy to lift, and so the cable can be done through that with a small jack operating at the top. And one of the things that we discovered, which made this a very attractive concept, was that we could actually build the top portion of the structure with this truss on top of the building, extrude the concrete floors, and then, like an elevator, lift that truss all the way to the 1,700-foot level. So you wouldn't have to have any cranes constructing the top of this thing, which was a big advantage in terms of safety. That's actually the reason, in the end, why this design was adopted over the alternatives, because of the safety of the design for construction. Back then, to conclude, with this tower, you know, I came back to this idea beginning of this year when it was obvious that things were slowing down at the World Trade Center. In fact, a few months later, this Freedom Tower, which had been mutilated by the governor, they finally realized that they couldn't really build it the way that they had changed it, and so they gave it up and came up with a new design. And that confusion seemed to me an opportunity to suggest again that maybe some of the needs that were there that needed to be fulfilled for the city could be satisfied in a different way. And coming back to this idea again of a structure that as you move around it is quite different, that has as much to do with the space between, which physically is important. The space between is the space the wind goes through. So that has significance, and also the possibility that you could arrange these stems in such a way that they're protecting each other in the direction from which the wind is coming. And so there's a geometry potential there that could actually reflect the environment. So there's a lot of, I think, aspects to this. The fact that the figures that you see from the beams connecting them also have themselves poetic quality. And so we're now developing this idea for a different location. We're thinking about seeing the possibility, part of this sort of relates to the discussion we were having earlier, of rethinking the New York area, not just as something concentrated around Manhattan. And I think part of the problem with the response to what happened in 2001 is that, you know, Manhattan being what it is, it's very narcissistic. And so it feels like everything is all about it. And in fact, what happened there is something that affected in the region, everyone that is around this harbor. It also is true that as the city grows and develops, there is more and more of a sense that it is a city that surrounds this harbor, and that our consciousness of that city is something that has to expand to encompass that region as a whole. And it seemed to me then that there was an opportunity to shift our thinking and to serve a purpose if we were to propose that this tower actually go not in Manhattan, but out in a site in the middle of the water, and then be situated in such a way that it would begin to establish a reorientation of our understanding of the New York Harbor in a way that could be, I think, very positive for the future. Thank you very much.
Thank you, Lee, and it was a superb lecture, and of course we really the honest perplexity in both the simplicity and complexity of your work. If you would like to receive a number of limited questions, because he has to leave soon to New York, he's quite busy, and he gave us a piece of his Sunday and early morning. Armando.
Working. Can you hear me well?
Yes.
In the same way that 9/11 has placed like a new need for rethinking structures of tall buildings, I think you touched lightly the recent event of Katrina. And I was wondering if you have been involved in urban or landscape projects and if you see any potential of a future of engineering landscape, in the same way as now the event of 9/11 has demanded new structures for tall buildings.
Definitely, yes. I think that the question of urbanism, and from my perspective of infrastructure, it became very important after 2001. And part of it is, I think that we live in a world where the fundamental motivation for decision seems to be the market and the economy, and the way we think about whether to go this way or that way as a society has a lot to do with economic welfare. And I think that in doing that, there's this presumption that there is somehow this natural mechanism of the market that will help us make good decisions, and that we can be more passive in relationship to that. I think these disasters that have happened recently in the US, but also, disasters that I've seen over the years after earthquakes, demonstrate that it also requires not just ideology, but design thinking to try to synthesize a situation and to propose different ways of thought. What I like about this last project, and when I've spoken about it with people in New York, is that you can suggest something physical and change people's minds and change their way of thinking about their home, their community, their economy, and so on. And that's where our engineers and architects have an opportunity. Because politicians don't have that training. They don't think that way. Economists don't think that way. Quick story. I have many friends from Iraq, and had the fortune, I guess, of knowing this Ahmed Chalabi from before. And so I've taken a big interest in what's been going on in Iraq, and in particular, the infrastructure. And one of the things that Chalabi is working on right now is trying to figure out ways to pump oil and get oil out of the country, but also generate electricity, etc. It's a big problem because of security, but it's also a big problem because of the collapse of the infrastructure under Saddam. Now, America comes in and not only invades the country, but also comes with a way of thinking about infrastructure. Halliburton, Bechtel, all of those organizations which do things in a particular way. Putting aside whether or not there's any corruption, even without corruption, there is intellectual corruption because there is no new way of thinking. These organizations have an ideology that really comes from the 40s and 50s and that hasn't changed. So I think then the actual physical infrastructure that is implemented under that way of thinking in a place like Iraq creates a foundation for the society, which the society may not want. And that is a domain that needs much more thought. There's a wonderful journalist who actually wrote in that magazine that I showed you from the New York Times. Half of it was devoted to this project that Bouchon did on architecture, and half of it was devoted to what became a book by a man named James Glantz, who's a reporter for the New York Times, on the World Trade Center. And Glantz was sent from Ground Zero to Iraq and has spent the last 2 years reporting on infrastructure in Iraq. And he's very interesting because he has, because of circumstances, thought about politics, infrastructure, and political change in infrastructure. It's, I think, a time that is not that different than the time when Bucky Fuller thought about how design could affect our way of thinking about social needs. And I think it's a time when architects and engineers really need to put in proportion their aesthetic interests and their desires as artists alongside these other political and social concerns, and try to bring them together productively.
Las preguntas se pueden hacer en español, por supuesto, y las traducimos para que...
Bueno, lo voy a hacer en español. ¿Cuál ha sido la experiencia de él en el diseño ecológico?
¿El diseño?
Ecológico.
Well, it's very related to what I was trying. It's very related to what I was trying to say. That you know, the question has to do with whether your design strategy is idealistic or empirical in a way. That the problem with infrastructure, the problem with the relationship between infrastructure and politics, and the problem with ecology is that we can't know what the right answer is. We build a road, you know, we came today along a road that has a traffic jam because of an intersection that was not skillfully planned. How do you anticipate that? Do you expect the traffic engineers to be smart enough to know with their modeling that they will do the right thing, or do you need to find a way to test somehow before you do, to find out whether or not what you want to do is a good thing? And I think with the ecology that's very important, that it's such a complex system that we have to be modest in the way that we design and test our designs to understand better and therefore make better designs. Rather than think that, I mean, for example, there are many proposals for doing things in buildings to make them green, but most of those proposals are design proposals, and they get built, and then everybody forgets about it. And I have yet to see any literature of people coming back to look at double wall that's supposed to help with the climate control of a building, testing whether or not it works. I know in Germany, Jörg Schleich told me that they're beginning to test some cabinet walls, and they find that they don't work. So what works and what doesn't work? And what used to work that we forgot about that works quite well, that we should adopt again. You know? So I think, particularly in that area, empiricism is fundamental.
Otra pregunta.
Hello. How soon do you think steel is going to be replaced by different materials such as ceramics or plastics or anything new that's going to be?
We had an interesting conversation about this at this seminar yesterday. I think behind your question is, if you will, a traditional modern view that new materials will revolutionize design. And I don't really ascribe to that view. I think what I was trying to show today, in a way, was an oppositional argument, which is that materials are not going to die and be replaced. Materials are not dinosaurs, and they won't go extinct, but they can be reinvented, and they can be used in ways alone or together that either recovers a historical idea that's powerful or creates a new combination that's powerful. But I don't personally believe that there is this sort of Hegelian progression that a new material replaces all the old materials, and there is therefore this radicalization in design. I don't buy it.
Dos preguntas más para que le demos tiempo a Guido que llegue al aeropuerto.
Is there any book in your private library that invokes the poetics of the structure and you can recommend us? That's the way you show the pictures of the comedies.
The question was, is there any book in my library that evokes the poetics of structure? Yes, there's many writings of Felix Candela the Spaniard Eduardo Torroja. More recently, Peter Rice, Nervi. We've all written a lot about that. Go ahead.
Do you have a novel in specific? Or what?
A novel. Good question.
A title.
Oh, a title or a novel?
No.
Like the Brothers Karamazov? No. I don't think anyone, I mean, Tolstoy writes about agriculture, but he doesn't write about, Tolstoy writes about agriculture, but not about structure. I don't think that you should write that novel.
Yo tengo mucho interés en los trabajos entre arquitectos e ingenieros. Encontré fascinante la estructura que nos mostró en Washington, donde la forma, la cubierta de este patio, donde la forma obedece a los diagramas de momentos, una correspondencia total de la forma con el trabajo mecánico estructural. Recientemente vimos una exposición del arquitecto Maximiliano Fuchsas sobre la Feria de Milán. Y recientemente ese mismo edificio fue presentado por George Schleich en una reunión de trabajo y nos decía que resolvió la estructura atendiendo a lo que el arquitecto quería, una forma totalmente libre. Y algo parecido está sucediendo con las obras de Fratelli, donde la forma de la estructura se convierte, o la estructura se convierte en esclava de la forma que desea el arquitecto. Mi pregunta sería, ¿qué sucede con esta arquitectura donde la forma es forzada, se resuelve, pero mecánicamente obedece un capricho del arquitecto?
There is definitely a tension, interesting tension in the last 10 years between the work of Fuchsas and Americans like Greg Lynn and others who make things in a sculptural way without any consideration of structure. And so the form comes before the structure. Sometimes the form is beautiful. And sometimes the form is not beautiful, but it is independent of the function of the structure. You mentioned Schleich, the very interesting collaboration that Schleich did with Frank Gehry, where they worked together on this project in Berlin for the Parisiplatz for this bank. And there you have this Schleich technique of using steel bars with cables that can create many different forms, which comes from originally the Mannheim Garden Festival Hall that Friado did, which, by the way, those of you who are looking for a good PhD subject, this Mannheim Festival Hall, which was designed by Otto Friado, was the first time that Otto did anything in compression. Everything he did was in tension, self-bubbles, so tension structures. And because it was in compression, he felt concerned that he might not understand all the problems, and so he invited Ove Arup to collaborate. And in Ove Arup's office at the time, there was Ted Happel, who later created a firm called Bureau Happel, and also Peter Rice. And so you have this unusual situation where this one project, which is a blob, I mean, it looks like, as good as any contemporary blob, involved Otto, Arup, Rice, and Happel with, I think, kind of on the side, though he said he had nothing to do with it, but on the side also Schleich. Schleich denies that he was part of it. it's a very important moment because from there, Happel and Rice began to develop their tension structure ideas. So historically, it's a very important moment, I think, that hasn't been studied enough. But anyway, so you have this tradition of Mannheim and other examples. You have these moments when someone coming out of that tradition works with someone like Gary, and you have this marriage of sculpture and structure. I believe that one has to have a broad enough critical sensibility to be able to say to Greg Lane, that's a good sculpture, that's a bad sculpture, and to discuss it, and to have a language with which you can discuss it as an engineer. At the same time that I would invite someone like Greg to talk about Mannheim and to describe how that work, or the work of Heinz Eisler, or other people who are disciplined in the way that they structure it, is from his perspective, positive or not positive. And that, I think, would then create more of a sense of the continuity between, abstract form and the interest that has, and concrete form, which is resistant because of the resistance of material. And I wouldn't make an opposition between the two. I would say sculpture and structure have a conversation that could be very positive.
Una última pregunta.
Muchas veces el costo de las construcciones limita los diseños que se pueden proponer. En el diseño que usted propone para el edificio en Nueva York, el hecho de generar un núcleo rígido al centro y de ahí bajar cables para los entrepisos, el hecho de mandar las fuerzas hacia arriba para luego bajarlas, no representa un costo que se divorcia un poquito con la posibilidad de hacer esas obras en cuanto a costo.
Yes, well, I mean that, before going there, just in response to the question about cost, which I think goes back to the discussion about economy. There's a great writer named J.B. Jackson who wrote actually wonderful books about landscape. He was a teacher of Robert Venturi, and I recommend, it's not a novel, but J.B. Jackson. One of his books is called The Necessity of Ruins. Beautiful title. But Jackson makes the distinction between vernacular architecture and monumental architecture. And I think for our monuments, we're willing to pay. And the work of Frank Gehry is a good example where different cities have decided that it's a good idea to build in Los Angeles the Disney Concert Hall, this extraordinary project, the Bilbao project, and so on. And many other examples like that where in extreme cases, the Hong Kong and Shanghai Bank that was built in Hong Kong to demonstrate the fact that the bank was not going anywhere. It was willing to spend $1 billion to demonstrate that it was staying in Hong Kong after the British left, because it was a Scottish bank. In other words, it was owned by Scottish people. So architecture and engineering have symbolic meaning sometimes, and cost is not really a consideration. Then in the vernacular world, which I think this belongs to, part of the argument that I was making with that project was that you could achieve something that was sculpturally strong and extremely economical. I mean, one of the tests was that the developer that I was working for would recognize that this was what he wanted to build because this was what he could build what he wanted for the least money. The way in which this project finally became adopted as the project for a while was because of cost considerations. The cable structure and all of that was actually very clever because it wasn't my idea, it was a colleague of mine came up with the idea, but that making that out of cable meant that you could take those columns and just make them like concrete silos, very simply slip-formed. And then the cables, as I showed, used very small equipment. So no cranes, very little danger, and a process that was small steps adding to big things. And so that's actually why that rational argument, their rational and cost related, was the reason why it was adopted. And it was also what I was trying to do, because I felt like there was so much irrationality and so much propaganda that was flying around, that here was an opportunity to come in and say, here's a reasoned argument, this is what reason is about. And reason can, even in this kind of chaotic situation, have an effect. I had no illusion that the building would be built. I don't think the building will ever be built. But to me, I saw this as a kind of performance act within the political arena of my city.
Bien, antes de finalizar esta presentación de Nordenson, me gustaría, antes de entregar el diploma por parte de la universidad, hacer una pequeña reflexión. Yo considero que uno de los objetivos, una de las misiones de la universidad es formar buenos profesionales que tengan a su alcance toda la información necesaria para poder realizarse una vez que estén graduados y aportar algo a la sociedad. Pero ser un buen profesional no implica únicamente conocer de su propio campo, sino ser un buen profesional implica ser un hombre culto, una mujer culta. Y allí es donde está, creo yo, el punto medular de lo que quisiéramos lograr en la formación de todos ustedes. Es decir, que lleguen a entender qué es lo que está pasando en el mundo. No podemos estar absortos a lo que está sucediendo en otras partes del mundo, en sus propias circunstancias, saber cómo, ¿verdad?, pueden evolucionar en este parteaguas que estamos viviendo actualmente en la humanidad. Yo creo que estamos muy conscientes de que hay un parteaguas importante por el desarrollo tecnológico tan fuerte que se ha dado en la última década, y ustedes, los jóvenes, son los que van a dar ese paso hacia adelante para entender el futuro de la arquitectura y de la ingeniería. Yo quiero, antes de dar la palabra, me dice José María, que aquellos grupos que no están conformados todavía para la Semana de Arquitectura permanezcan en esta sala para organizarse, y quisiera aprovechar este momento para dar las gracias a Víctor Márquez como coordinador del Diplomado, a Patricia Álvarez, a Benjamín Romano, a todos los que han colaborado para traer a Nordenson. Y quiero felicitar a Nordenson por esta ponencia extraordinaria, es decir, cómo nos relaciona con la historia, cómo nos relaciona con otras artes, con la escultura, con la pintura, y cómo su interés también por llegar a entender el mundo en toda su verdadera comprensión. Eso yo creo que es algo muy importante, es decir, para reconocer en una escuela de arquitectura a un ingeniero que tiene esa sensibilidad. Muchas gracias, G. Y hay que
hacer